Hello, everybody, and welcome to organic chemistry. All right, we're going to do a short unit on organic chemistry and the carbon cycle. So at the beginning of your notes here are all of the different terms having to do with organic chemistry. All right, so remember, organic chemistry is the study of carbon compounds. All right, so carbon is our main element that we're dealing with. So the study of carbon compounds. But in addition to that, all organic compounds technically have hydrogen as well. All right. They certainly can have other elements, and they do, things like oxygen, nitrogen, all right, and actually several others. But these are our two big ones, okay? All right, so we're just going to talk about being able to name and write the formulas and draw the structures for some simple organic compounds. The names for organic compounds are based on the number of carbons. All right, and we use special prefixes for these. And these prefixes, again, tell you the number of carbon atoms in the particular compound. The prefixes are meth, eth, prop, bute, pent, hex, hept, oct, non, and dec. All right. Certainly there are organic compounds that are even larger, okay? But these are the ones we are going to stick with. So please make sure that you are very, very comfortable with these prefixes. Okay. So we are going to start out with the simplest type of organic compound, and these are known as simple hydrocarbons. And specifically, these are saturated simple hydrocarbons, all right? Now, the words saturated and unsaturated should sound familiar to you because of just kind of everyday talk of saturated and unsaturated fats. And that is actually exactly where they get this concept of saturated and unsaturated fats from the structure of the organic molecule. Saturated means as many hydrogens as possible around the carbons. So another way of saying that is that all of the carbon-to-carbon bonds are single bonds. You have no double or triple bonds, okay? So let's see how this is going to work. Before we go on, please remember that carbon needs 4 bonds around it. This is super important, so we're going to put big stars here. Carbon must have 4 bonds, and hydrogen is only going to have that 1 bond. All right, if you recall from the video we watched, and he talked about you're good as long as you can remember 1, 2, 3, 4 and misspell hunk, because hydrogen just needs 1 bond, oxygen 2, nitrogen 3, and carbon 4. All right, so we're going to start out dealing with just hydrogen and carbon right now, but that is a nice little clue to keep you going. All right, so saturated simple hydrocarbons are known as alkanes, and all of their names are going to end in A-N-E. All right, so A-N-E because it is an alkane. Now, I'm going to show you a couple different ways of showing me this molecule. All right. So first there's this little equation that you can use, and this works for any alkane. All right. And that's CnH2n plus 2. Now, what are those N's there? The N's just represent the number of carbons. All right. So the N is the number of carbon. And where do we get that from? We get that from the prefix. All right. So I'm starting with propane. Well, the prefix prop, you'll go back to your list, you'll see that prop is 3. So that means that I have 3 carbons. And then to figure out my hydrogens, I go 2 times 3 plus 2. So that's going to be H8. But I'll tell you, you actually don't need that little formula, all right, because there's another way to do this as long as you remember carbon needs 4 bonds and hydrogen needs 1. If I were to look at the name, propane, all right, I know it's prop, so that means I have 3 carbons. So I'm going to go ahead, 1, 2, 3 carbons bonded to each other like that. Ane, A-N-E, tells me that it's all single bonds, so my bonds are good to go. And then I know that carbon needs to have 4 bonds. So all around there, I am going to bond those carbons 2 hydrogen. All right, I could then go on ahead and count up what I have. I have 3 carbons, and then I have 3, 6, 7, 8 hydrogens. All right, so these two are both formulas for propane. This is a molecular formula, and we're used to using those. We've been using those all year. All right, so this is the molecular formula. What I have here is what's known as the structural formula. And structural formulas are really important in organic chemistry. Okay, and we're going to see that as we move on. Okay, so why don't you go on ahead and pause the video and tell me the molecular and the structural formula for heptane. All right, so heptane, hept is 7, so that means I'm going to have C7H. I can just use my little equation because it's right there. So C7H16, and to double check, here's my structural formula: 1, 2, 3, 4, 5, 6, 7. All right, and then my hydrogens coming all around. Now, as a shortcut, all right, I am going to leave without drawing all those hydrogens in. We know they're there because carbon has to be bonded to 4 things, and we know right now we're only dealing with carbons and hydrogens. But just as a shortcut, I'm not going to draw in all of those H's. In organic chemistry, there are a lot of shortcuts. Okay, so just so you know, although you are not expected to necessarily be able to do this, the shortcut, the proper way in organic chemistry to draw this is just like 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. That would be all you would actually draw for heptane, because every point, every time a line either ends or comes together, that is a carbon. And we assume that they are surrounded by hydrogens. So just to kind of let you know the different things going on there with the ways we can draw those structural formulas. All right, so alkanes are saturated, meaning they have as many hydrogens as possible. Okay, but once you get multiple bonds, those can be double or triple bonds, we say that the molecule is unsaturated. All right, and when you have an unsaturated hydrocarbon, that means you have a double or triple bond, and you have to let the person know who's reading your formula or your name, you need to let them know where that double or triple bond is going to be. And we do this by using numbers. All right, so let's see what this is going to look like. If you're dealing with a double bond, it means you have an alkene, and the name is going to end in ENE. All right, the equation for an alkene is just simply CnH2n. All right, and again, when you see these numbers in these in the names, that's telling you where the double bond is. How do you know it's a double bond? It ends in ENE. So let's go on ahead and start with 1-butene. Well, I'm going to start by using my prefix. So you're going to look at your sheet, and but is 4. So that means you're going to have 4 carbons, 1, 2, 3, 4. There is a double bond. You know that because it ends in ENE. And where is that double bond located? It's located off of the first carbon. Now, this is where things get sort of interesting. Well, the first carbon, we're used to reading from left to right, and that's totally fine. All right, so right there, I would put a double bond. Okay, great. And now I'm going to go on ahead and give the carbon all of its hydrogens it needs. My end one over here needs 3, you need 2. Now watch out. This carbon here already has 1, 2, and 3. So it just needs 1. Doesn't matter whether you want to put that on the top or the bottom. This carbon already has 1, 2. So it needs to have 2. All right. Again, we just try to make things look symmetrical. Don't worry so much about where the direction things are going. Okay. So now all of my carbons have what they need, and this would be 1-butene. Or, now here again is where things get fun. There's no rule that we have to read from left to right. this is also 1-butene. Okay, I just kind of flipped them, and that's totally acceptable. Both of these are acceptable structural formulas for 1-butene. The molecular formula for 1-butene is just simply C4 and then 1, 2, 3, 4, 5, 6, 7, 8, H8. All right, let's go ahead and why don't you take a second and do the 3-octene. Okay. All righty, so octene, oct meaning 8, so I'm gonna have, it's gonna be C8, H16, so we're gonna go 1, 2, 3, 4, 5, 6, 7, and 8. All right, 3 means that my double bond is off of the third carbon, so I'm gonna start here. All right, 1, 2, 3, so right there is gonna be where my double bond is. All right, you don't want to put it between the second and the third because then that would be 2-octene. So you want it after whatever the number is, 1, 2, 3-octene. And then I would go on ahead and do my sticks for my hydrogen. Again, being careful, this one already has 2. So that's all it needs. This one already has 3, okay? Or I'm sorry, this one already had 3, so I only need 1. And we just go, and then we want to double check. And when we do, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and it matches our formula. Okay, great. So now we're going to move on to the alkynes, and that's how you say it, alkyne. All right, and this, an alkyne, has a triple bond, and the name is going to end in YNE. All right, so your simple little equation for alkynes is CnH2n minus 2. You can see as we use multiple bonds, the number of hydrogens is reducing. All right, so let's go ahead and look at our examples. I have 1 pentyne. Well, pent means that there's 5 carbons, right? So 1, 2, 3, 4, and 5. 1 tells me that the triple bond is coming off of the first carbon. You may choose either one to be your first carbon. I usually choose the one on the left, but that's just habit. It doesn't really mean anything. All right, so there's my triple bond. Okay, well, now we're gonna give everything its hydrogens. Well, this carbon already has 3, so it only needs 1. This second carbon, 1, 2, 3, already has 4. It gets none. Then this one gets 2, and boop, boop, boop. So to give me C5H, 1, 2, 3, 4, 5, 6, 7, 8. And that makes sense because our formula was CnH2n minus 2. Well, 2n would be 10 minus 2 is 8. So that works out great. All right, go on ahead and pause and please give me the structural and molecular formula for 3-nonine. Okay, great. So known or non, but usually say it known, is 9. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, and 9. We're just going to double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Great. 3 means that my triple bond's coming off the third carbon. I'm going to make this carbon number 1, 2, and 3. Here we go. There's a triple bond. Okay. So now I'm going to give my hydrogens. This carbon already has 4. This carbon already has 4. Great. And so I am C9H, and we know what it should be, but let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Perfect. And that's what it should be because 2 times 9 is 18, minus 2 is 16. Okay. All right, fantastic. Now, when we draw out molecules like this, things like 3-nonine and 1-pentyne, these are called chains. And they're called chains because they just kind of go in a straight line for a while, right? They just keep going. What an interesting thing about organic compounds, and a reason why we can get so many different types of them, is you can also have what are known as rings. All right, so organic compounds can be found as chains, as we saw above, or as rings. And we know we're dealing with a ring when we see the prefix cyclo. All right, so the prefix cyclo. Okay, so cyclopentane. Okay, so we're going to dissect this. So pent means 5. So I have a 5 carbon ring because it starts with cyclo. Okay, so that tells me it's a ring. Pent tells me it's 5. And then the ANE tells me that it's all single bonds. All right, so cyclopentane, I'm going to have 5 carbons in a ring. Now, typically these take the shape of what you think they would. So for 5, that would be a pentagon. Don't worry so much about the shapes. Just do the best you can with them. A pentagon is kind of one of the few shapes I can sort of draw. So we're going to go ahead and do that. It's not a great one, but you get the idea. So I have a 5-sided ring. All right, and each of the carbons already has 2 bonds because they're bonded to each other. And so each get 2 hydrogens. So for cyclopentane, I am C5H10. All right, so you might notice or be thinking, okay, well, C5H10, that's also the formula for pentene, right? So we have a situation where we have a molecular formula, all right, that is the same for 2 very different looking molecules, because this could be, as we just saw, cyclopentane, or it could be just simply pentene, all right, which is just 1, 2, 3, 4, and 5, and let's just say it's 1 pentene, okay, to give us the double bond there. And then we're going to have, there we go. So both of these are C5H10. When that happens, when you have the same molecular formulas but different structural formulas, we call these isomers, and that's an important term. Okay, again, this is the same molecular formula, but a different, or we'll just say but different, structural formulas. And this is incredibly important in organic chemistry. It comes up all of the time. And this is why being able to draw these structures is so important, because just simply saying C5H10 does not give us enough information. There are multiple types of isomers out there in organic chemistry. All right. Next up is the special molecule called benzene, and this is one that just simply goes by its common name, benzene. We don't name it using the prefixes or anything like that. And this is all molecules that are known as aromatics, which is really, it's just a very large category of organic compounds, contain a benzene ring. So it's important for us to know what a benzene ring is. Well, the formula is C6H6. It is a 6-carbon ring. So I'm going to be nice and careful drawing this. Try to make it as pretty as possible. Okay, great. All right, so you have a 6-carbon ring there. And you have what is known as alternating double and single bonds. So between every other carbon, you are going to have a double bond. All right, just like that. And then there are hydrogens on each of the carbons, because if you notice now, each of the carbons has 1, 2, 3 bonds, so they each need 1 more. And that gives us the formula C6H6, and that is benzene. Benzene also has some shortcuts as far as how you draw them. All right, you can draw benzene, and this is kind of the most common way of seeing benzene, is like this. Like that, okay, that is benzene. A more old-fashioned way, but is still used in some textbooks and things, is to draw it like that. Again, this benzene ring is part of a large, is a part of a very large category of organic compounds known as aromatics. All right, and all aromatics have a benzene ring in them. All right, great. So far we have just talked about what are known as simple hydrocarbons, compounds that just have carbons and hydrogens in them. All right, in organic chemistry, as far as when you add other elements, all right, and those other elements can be very different elements. When you add other elements, you get what are known as functional groups. All right, functional groups are another reason why we get such a diverse amount of organic compounds. There are lots of different functional groups, but we're going to only go over 2 of them. All right. Okay, so the first one we're going to talk about are alcohols. Okay, alcohols contain what is known as a hydroxyl group. So that means it is going to be whatever your carbons are, and then it's going to have, one of the carbons is going to have an OH next to it. Now, please be careful. A hydroxyl group is not the same thing as a hydroxide ion. All right, hydroxide ions are in ionic compounds. Organic compounds are covalent. Okay, but this is our hydroxyl group. It is, you're going to have a carbon and it's going to be bonded to an oxygen, which is bonded to a hydrogen. Remember, oxygens want only 2 bonds. Okay, alcohols all end in the ending OL. All right, and you can get some different types of ones that you certainly have heard of before. All right, so for example, let's start out with 1-propanol. Okay, so just like with our other organic compounds, we're going to look at this root to tell us what is going on as far as the number of carbons. And prop is 3, so that means I have 1, 2, 3 carbons. The 1 tells us where the hydroxyl group will go. We know it's an alcohol because it ends in OL. We know all alcohols have a hydroxyl group. Where does that hydroxyl group live? It lives off of the first carbon. All right, so again, as you are writing these, you're the one writing them, so you can decide which carbon is carbon number 1 or number 2. You could make it the left. Typically with alcohols, we make it the one on the right. It's not a strong rule though. You don't have to. All right, remember, hydrogen only wants 1 bond. You do have to write this hydrogen in. It's not like these where we can just take a shortcut and leave them out. You have to have that hydrogen next to the oxygen, and then a single bond between the oxygen and the carbon. And that would be 1-propanol. You could also, as I was saying, make this one your first one, but then you would have to flip the O and the H because it's the oxygen that has to be between the hydrogen and the carbon. All right, so either one of those would be totally fine for 1-propanol. If you were to have the hydroxyl group coming off of the second carbon, you would be dealing with 2-propanol. Okay. All right, so now let's go on ahead and talk about ethanol. Ethanol is used for a lot of different things. One of them is what we known as drinking alcohol. All right, but ethanol is also used for a fuel, lots of different things. Eth means that there's 2 carbons, so 1, 2. You might notice there's no number with ethanol, and that's because either one of these carbons would be considered the first one. All right, so that's why we do not include a number. If you did include a number, it would be 1-ethanol, but that is the only place you can have the ethanol, as either one of those would be considered the first carbon. So that is ethanol. All right. The second functional group that we are going to deal with is what's known as carboxylic acids. Carboxylic acids are a large group of compounds that kind of range all sorts of things. Insect stings are caused by carboxylic acids. Vinegar that we drink, which is known as acetic acid, is a carboxylic acid. All right. All of these, their names are going to end in oic acid. So and then acid. They contain what's known as a carboxyl group. And a carboxyl group is this. It is a carbon that is double bonded to an oxygen, single bonded to a hydroxyl. All right. And this carboxyl group is known as a terminal functional group. And what that means is that it must be on the end of the molecule. So always at the end of the molecule. All right. So butanoic acid. All right. So butanoic, but, our prefix but is 4. So that means I'm going to have 1, 2, 3, 4. Off of that fourth, double bonded to an O, single bonded to an OH. All right, and that is my formula for butanoic acid. Now, for drawing the molecular formula for this one, what we do is actually this. It's a little awkward, but C3H7. Well, where am I getting that from? Well, I'm talking about what's going on over on this side. I have C3H7 and then COOH. Now, we write it like this to tell the reader we're dealing with a carboxylic acid. You certainly could write this as C4H8O2. That would be totally accurate. But this is just kind of a way to give a little bit more information in a molecular formula. All right. So octanoic acid is next. So why don't you go ahead and pause and give that one a try. All right. So oct is 8. So 1, 2, 3, 4, 5, 6, 7, and 8. Double bond O, single OH. And then giving all my carbons their hydrogens. You can see why we take shortcuts for this because it can take so long. All right. And then this one would be C7H15COOH. Okay. The last thing we are going to talk about for our organic naming and formula writing is you can have what are known as, well, before we get to that, we can also have other elements coming off of longer chains. And if that happens, all right, particularly things like halogens, which is what we're going to be dealing with, off of that longer chain. A halogen, remember group 17, they only want one bond too. Okay, so keep that in mind. So you can have simple hydrocarbons that are on longer chains. You can also have other carbons. So let's see what I'm talking about with this. All right, just a little warning, don't get too overwhelmed. We're going to do a lot of practice with this. All right, but this is just kind of all little fun things that can happen. All right, 2,3-dimethylhexane. Okay, that's a lot to deal with. Break it down. Start with the part you know, hexane. All right, so our prefix hex, okay, we double check, and hex is 6. And ANE means that it doesn't have any double bonds. So I'm going to go ahead 1, 2, 3, 4, 5, and 6. Great. ANE means no double bonds. I don't have to worry about that. 2,3-dimethyl. All right. Anytime you see something ending with this YL, it means that it is what's known as a side chain or a branch. Okay. So side chain, also known as a branch. And it means that it's coming off of the second and the third carbon. All right. So the di just means that there's 2 methyl groups. What's a methyl group? Well, meth is a single carbon, right? According to our prefixes, meth is a single carbon. So that means I have a single carbon coming off of my second and my third carbons. So here we go. I'm just going to start numbering from the left because I'm the one drawing it, so I can do that. So here's my second carbon. I'm going to put a meth, which is just a single carbon. Then off of my third carbon, I'm going to do the same. And now boom, 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 boom. Why am I putting hydrogens? Because hydrogens are always circling those carbons to give them 4 bonds if they don't already have it. And that would be our 2,3-dimethylhexane. All right, let's check out our letter B. All right, 4-ethyl, 2,3-dichloro, 1-decanol. Okay, start at the end. That's what you're going to know. At least that's the one that should be the easiest. So dec means 10, ane means no double bonds, and OL means it's an alcohol. So let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I have my 10 carbon chain. It's 1-decanol. And remember, alcohols, we usually put the hydroxyl group at the right, which means that this is now my carbon number 1. Keep this in mind. Once I make this carbon 1, I have to follow that throughout. So that's carbon 1, 2. You wouldn't really write this if you were writing an answer, but just to keep us straight on our carbons. All right. So 1-decanol, check, done. 2,3-dichloro. So that means I have a chlorine atom. Di means I have 2 total. Where are they? They're off of the 2nd and the 3rd. So here we go. I'm going to put a chlorine there. Remember, halogens only want 1 bond. And then I'm going to put a chlorine here. Why do I put them on each side? It just makes it look nicer. Okay. And then chlorines are fine. You don't do anything else with them. Okay. So check. All right. 4-ethyl. All right. So off of my 4th carbon, I have an ethyl side chain coming off. So here's my 4th carbon. Eth, you're going to check your prefixes, and eth is 2. So off of that 4th carbon, I have 1, 2. That is an ethyl side chain. And now I start adding all of my hydrogens. Sorry with those numbers, it's a little hard to see. And there we go. All right. We're going to have a lot of practice with this, so don't worry if it's not super clear right now. Okay. Have a great one.